Hello again and welcome to another Docker tutorial. I will be talking about Docker networking options. So if you want to get past the very familiar port publishing option, then this lesson might be for you, and I hope you will find some interesting info. So let's go to my gray board here and start drawing a couple of things. Just 1 second. All right. I will be talking about the options that you have with the bridge networking driver. So let's start and represent our bridge here. This is a software bridge, let's say in a Linux host. All right, like this, and it has 3 ports down here. 1, 2, 3. And these ports are connected to some container applications. I have app 1 right here, app 2, and app 3. All right, and these are the connections. These connections, as you might already know, are VETH connections, VETH. Let me write it down here. VETH. So these VET connections are specific to Linux, and they are coming in pairs, and they have one leg over here in the switch and one leg in the container. All right, let me delete this because I don't need it. And let's put an IP address class on this broadcast domain. Actually, let's say we have here 172.1.1.0/24. All right, and the containers also have the IPs from this class. Let's say app1 has .11, app2 has .12, and app3 has .13. All right, and as you might know, these Linux bridges are represented in the system as an interface. There is actually this master interface, and the other interfaces are slave interfaces. So I will represent this interface here with a different color. So in Linux, when you will display your bridges, you will see the master interface. And let me call this let's say BR0. So this is actually my interface. It's also a layer 3 interface that represents the bridge. And all of these green interfaces are slave interface. Anyway, what you need to take from this is that on this bridge, on this multi-port bridge, I have a special interface which is a layer 3 interface and has an IP. And the IP of this interface is from this class 172.1.1.0/24, and I will say it's .1, not like this, like this. So this will function as the default gateway for all these containers over here. And let's imagine the boundaries of my Linux host here, and I will represent it also with a different color. And let's do it like this. It's going a bit over what I wrote here. Anyway, so everything that's inside this box is belonging to the physical host. So this interface is here, the green ones and the blue one are, you can display them in the actual Linux host. So what do we miss here? What we need? This host, of course, needs to have access to the outside physical world, physical network. This network right here. And for this to happen, it will have another interface. And let's call this interface ETH 0. All right. And this interface is connected to this physical network. All right. And what IP addresses do we have here? We have this. Let's put it also in blue. Give me a second. Here we have 192. That 168. That 122. That 0/24. All right, and let me move this title a bit upper, like this. And the IP of this interface, the one in my Linux host, is .10. All right. And one last thing that I want to represent in here is a router. Actually, this being a normal TCP/IP implementation inside my Linux host here, I also have routing. There's a routing process that has these interfaces ETH0 and BR0. All right. Let me make it a bit smaller. So what are those options that before that my goal with this is to have packets from this network forwarded to the apps right here. All right, so what are the options that that I have? First option, let me take a different color. Let me put it with this. First option that I have, number 1. It's the very popular that maybe is used in more than 90% of the time, is the NAT or port forwarding. Sometimes it's called PAT, port address translation. So how does this actually, like this? I will explain it in a moment how it works. The second option is routing. And the third option is bridging. So I can route, and then I can do bridging. And let's take this one by one and explain them. I will copy this drawing and place it right here. So we are discussing the first option, NAT and PAT. All right. So what I do usually with in this case, I start my containers using the -p or publish option, and specify the ports that I want to publish. Something like this. For app1, let's say, I will use the -p, and let's say for port 81 on physical host, I want to forward traffic on port 80 to my app1 container. For app2, the same, or similar, not quite the same. App2 -p, that this time 82, because I need another port that is not used on my physical host, and 81 is already used by the first rule, and it's sending the traffic to port 80 on the container app2. This can happen because here I have inside my Linux host, I have also IP tables running, and this IP tables is doing the netting. And let's try and imagine how things are actually working from the end to end, from the user that wants to access the container. And I will represent here a couple of user PCs. Okay, let's say I have here my PC1 and here my PC2. And if I want to access container, let's say app3, this one right here with the .13, I didn't put a number. I want to access app3 from PC2. How do I do that? Let's say I have a NAT rule from port 83 to port 80 for app 3. I will actually send traffic to this interface. So my traffic will be, I will open a connection to 192 168 dot 122 dot 10, like this. And my traffic, and actually on port, let's say 83, I have the publishing rule for app 3 on port 83. Let me write it here to be clear for everyone. App 3 is published on port 83 on my Linux host. So any traffic that reaches my ETH0 interface on that IP on port 83 will be, let's say here is port 83, will be forwarded here on port 80. The choosing of these ports is totally up to the situation and your needs. Sometimes you can, if you have only one container app, you can choose to publish port 80 on the physical host and go to port 80 on the Linux container. But sometimes, or actually most of the times, port 80 on the physical host or on the Linux host might be already busy with or occupied by other service. So this is how things are working for the first scenario, NAT. I hope it's clear. Let me take again my copy again my drawing here and go to the second scenario. Not like this. All right. All right. So right now we are discussing the scenario, the second scenario, the routing. For the routing, let's again imagine that we have a couple of computers on this physical segment here in the upper area. So I have my PC 1 and also my other PC 2. Actually, before talking about computers on the physical network, let's imagine that we are trying to ping app 3 from the Linux host itself. Do you think it would work? Let's say here app 3. If I'm trying to ping it from here, the answer is, of course, yes, it will work, because the packet will be originated from this host with the source IP of BR0. So it will go from here, with the source IP of BR0, so 172.1.1.1, and it will go directly to the .13 IP, because it's a directly connected route. That's the main idea, the key point here to understand. Both networks are directly connected on this host, and if you try to ping from the host itself, of course, it will have a route in the routing table, and it will send packets directly to the BR0 interface. But of course, in the real world, I will need to access those containers from outside. So from PC1 and PC2 and whatever other PCs I have there. So what I can do is add routes. If I'm trying to ping from PC1, PC1 will not be able to reach 172.1.1 because it doesn't know how to get there. It needs a route. So what I can do is add a custom route here on my PC1 and on my PC2 and all the other PCs on this network. But this will become tedious if I have many PCs. So my next best option, and actually my first best option, is to go to the default gateway of this segment. Each network like this will have a default gateway that can take users to the great beyond internet and some other networks. Anyway, and also I told you in the first that PC1 and PC2 do not know how to route to 172.1.1.0, how to get there, because the only route that they have normally is the default gateway. Let's say this is the .1 address, and all they know is how to get here to this gateway, and for any network that they want to reach, they will ask this gateway. So the best option is to have this route for 172.1.1.0 to add it here on this default gateway, and the traffic will flow like this. Let's say PC2 is trying to access F3 container, and it will give the packet to this guy, and this guy, it will say it will actually send an ICMP request, not a request, an ICMP redirect message to PC2, and it will say update your routing table because the next hop for 172.1.1.0 is in the same broadcast domain, and you can reach it directly without going through me as the next hop. So in that moment, PC2 will update its routing table, and it will be able to forward, to send the traffic to the containers, and it will send the traffic to the IP with .10, so 192.168.122.10. I mentioned ICMP redirect. It's not a big deal, and you don't have to think too much about it. It might not happen like this. You might have another network over here, let's say, I don't know, another physical network like this, and if traffic will flow from here, it will not happen with ICMP redirect because the next hop will be on another network. doesn't matter. I told you about ICMP Redirect because in the hands-on lab that I will follow up to this tutorial, I will have this scenario with ICMP Redirect. So that, but it's not important at all from the perspective of understanding the routing mechanism that I have explained. So we have one last option. Let me show it to you, or discuss it actually. The bridging. So again, let's copy this and go like this somewhere here and paste it. All right, and we're discussing scenario 3, bridging. And this is actually very simple to explain. Actually, it's simple. I don't know if it's actually very simple. So if we are doing bridging, I will delete the router here. And what I want actually is to have this ETH0 interface, have it as a slave interface to my Linux bridge. So actually with the green color. So now my ETH0 will be part of, I will make it part of my bridge here. So this one here is ETH0, and it has the, actually, yes, it will have the .10 IP, and there's another thing that will happen. I cannot have this, or I cannot have actually a different IP class on my Linux bridge. I will have the same broadcast domain of this physical network, 192.168.122.0/24. It will span over my virtual bridge over here. So let's delete these numbers. Let's keep this line. And what I have now, actually I did it wrong. ETH0 is just a normal slave interface on my virtual bridge over here, and the virtual bridge, the software bridge, it has the .10 address. Let's put it right here, and let's delete this. So now my traffic right now will flow like this. From this physical network, it will go to the physical connected interface, ETH0, and from there it will be able to reach any of those containers, that 11, 12, and 13. I still need an IP address here because this IP address will be used when I want to send traffic to this physical or to this Linux host. Other ways, I don't need this, but this is how bridging works. If I'm taking my physical interface, which is my link with the physical network, and it has an IP address, and if I take this and I enslave it to the software bridge, the IP address here will disappear, and I will be left only with the IP address on the software bridge interface. So again, let's represent here, let's say a PC1. It's enough for this. And if I want to send traffic from PC1 to, let's say, this container, this app3 container, what I do is just do what will happen. The IP address will be mapped with the MAC address through a ARP request, and that's it. All right, I think it's enough for this session, and I will follow up with some hands-on lessons, and I will show you how things are actually configured, and hope this has been useful, and see you in the next lesson. Bye bye.